Hi, and welcome to the lesson of real analysis. So, in this class, we are going to start a new chapter that is sequences. So, we talk about real numbers, their properties, and sets of real numbers, natural numbers, rational numbers, and some other sets. And we find their limit points, interior points, their bounds, upper and lower bounds, their isolated points, adherent points, and closures of the set. Now we will take on this chapter, that is sequences, and we will use all the results that we derived in the earlier sections. So let's start with the definition of the sequences. It says that infinite succession of numbers, not necessarily different. So it's not a rigorous definition, it's just an intuition that the sequences are infinite successions of numbers, and it's not necessary that the numbers are different. So what do we mean by this statement, that infinite succession of numbers? So for instance, if we are talking about this sequence, -1 over n, -1 to the power n over n. So this is a sequence. Then we can plot its points on the line, -1 over 1, then 1 over 2, then -1 over 3, then 1 over 4, and so on. So we can see that this is infinite. There are infinite numbers, and we can see the succession that after every number we have a number. So after each number we are getting a number, and to infinite terms we have. So this is infinite succession of number, not necessarily different. So what do we mean by this, that not necessarily different? So if we talk about this sequence, that is 1 to the power n, we know that it's a constant sequence. We will get 1 1 1 1 1 1 infinite times, and we call it an infinite sequence and a constant sequence. So it's not necessary that the terms are different, like in this case, that each term is different from the other. So a sequence, terms of the sequence may be same, may not be same, but this is necessary that they are infinite. Okay, but it's not a rigorous definition. Let's talk about the actual definition of the sequence. It says that a sequence of real numbers is a function that maps, that is x, such that it maps natural numbers to real numbers. Okay, we will define this, we will elaborate this. That is, given any natural number and there is a corresponding real number. Okay, so if again, if we consider this sequence, that is -1 over 1 n, and we can see that the input of this sequence is from the natural numbers. And for every sequence that we are going to talk about in this section of real analysis, that the input is from the natural numbers, and what we are getting is a real number. For instance, if I take n as 1, starting with 1, we get -1 over 1, then -1 over 2, sorry, +1 over 2, then -1 over 3, then +1 over 4. So these all are the real numbers. They are not naturals. So these all are the real numbers. So we are taking input from the natural numbers and we are getting output in the real numbers. So that's the exact and actual definition of this sequence, that it is a function that maps natural numbers to real numbers. And we represent this sequence by xn in this curly bracket form, or occasionally we can write it this way as well, that xn n equals 1 to infinity. So the sequence, the terms of the sequence can be laid down in this way, that xn equals x1, x2, x3, x and dot 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 to xn plus 1. Now, strictly speaking, a sequence need not have infinitely many different terms. Okay, we already talked about that it's not necessary that the terms of the sequence are different. So we need not to have infinitely many different terms, since some or all of them may be the same. For instance, we talk about the constant sequence, that if we have 1 to the power n, then we are going to get 1 1 1 1, and that is a sequence, and it's a constant sequence in fact. And the terms are same and they are infinite. And we may have a sequence like this: 1 1 over 2, again 1 1 over 3, again 1 1 over 4, again 1 1 over 5, and this is also a sequence, right? So the terms of the sequence can be repeated. The terms can be repeated in the sequence, so it's not necessary that they are all the terms are different in a sequence. Let's talk about an example that a sequence is given by this function, that is xn equals 2 plus bracket -1 to the power n over n, and we write some few terms of this sequence on the real line. So its first term is 2 minus 1 over 1, then 2 plus 1 over 2, then 2 minus 1 over 3, 2 plus 1 over 4. So we have 1, 2, 3, 4, 5. So we have first 5 terms of the sequence. And if we just simplify these terms, we get this thing here: 1 comma 5 over 2 comma 5 over 3, 9 over 4, 9 over 5, and so on. And if we plot this on a coordinate system, say n and y, and we take as 1 here, for instance, 2 here, 3 here, 4 here, 5 here, 6 here, and so on, then we are going to see that the numbers are converging near 2. So the numbers are getting closer and closer to 2. So we can observe that the line that we have drawn here, that is y equals to 2, this line, this is line that is y equals 2, is an asymptote for all these numbers. So we already know about the asymptote. It's a line that moves with the curve to infinity, and it's a straight line, in fact. So observe that the line y equals 2 is an asymptote. We thus say that the sequence xn converges to the number 2 as the limit. So in this case, we can easily say that the sequence is converging to the point 2. Because as we move towards infinity, we are going nearer and nearer to 2, and we can see here in this case that is 9 over 5. Then we will have sorry, yes, it's 9 over 5, and then if we want to get the other term, it will be 2 plus 1 over 6, that is 13 over 6, and we are moving closer to closer and closer to uh 2. Okay, so now we will talk about the definition of the limit of a sequence. Okay, so let xn be a sequence. So we have a sequence that is xn, be a real number, and L be a real number. Okay, we talk about L, that is the limit, be a real number. Then now this definition is very important, and each term of this definition is really important. So we are saying that limit n tends to infinity xn equals to L if for each epsilon greater than 0. So whatever epsilon we want to take greater than the 0, very close to 0, we can take any epsilon very close to 0, but it will be greater than 0. Then there exists an n naught. So there exists some natural number n naught that will belong to n, such that for all n belongs to natural numbers. This thing here is not very necessary to write here, but we are writing for the understanding purpose. Then such that for all n belongs to n, when this n is bigger than or equals to this n naught, it will imply that xn minus L is now less than epsilon. So what does it actually mean? So For instance, if we talk about the sequence, let's say 1 over n, this is a sequence. So xn equals 1 over n. So we can write the terms of the sequence 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. Now, the limit of, okay, I'm claiming that the limit n tends to infinity, 1 over n equals 0. So what do we mean by this definition for this limit here is that as I am moving forward, going bigger and bigger, the distances the distances between this number and this limit, that is 0, I am claiming here, L equals 0, the distances are becoming smaller and smaller. So if I subtract 1 over 2 minus 0, for instance, if I subtract 1 minus 0, I will get 1. If I subtract 1 over 2 minus 0, that is this definition, xn minus L, we are claiming. So we are taking all the elements of the sequence. For instance, if I take x1 and I call x1 minus L, for instance, so what I am going to get is 1 minus 0, that is 1. Okay. And when I take x2 minus L, so I'm going to get x2 is half. So half minus 0 is half, equals to half. And when I take x3 minus L, so that is equals to 1 over 3 minus 0. So I get 1 over 3. And I can see that these distances are becoming lesser and lesser as I am moving on and on. And then there will be some n, according to the definition, there will be some n naught. We are calling that thing n naught. So there will be some number of the sequence. For instance, this is the first number of the sequence, this is the second number of the sequence, this is third number of the sequence, this is fourth number of the sequence, this is fifth, this is sixth, and as I'm moving on and on, so I have lot of numbers, infinite numbers in the sequence. So there is some number, it maybe it's a hundredth number, it's thousandth number, it's 1 millionth number, or 1 billionth, or 1 trillionth number. So there is some n naught, there is some n naught, that after that n naught, whatever n I have, this thing here, that n greater than equals to n naught. So after that n naught, whatever n I take, and take the difference with the limit in the absolute, in the mod, I will get a number that will be less than epsilon. Okay, so epsilon is a number that I can think as small as I can, but it's bigger than 0, and as small as I can think about it. So it's a positive. So it may be 0 point trillion times 0, and then some number. It may be trillion of trillion times 0, and then some number 1. So it's like a very, very small number, very close to 0 epsilon. So the distance is the definition, that it says that simply that the distances, as we go bigger and bigger, far and far, the distances are becoming small and small and small, and they are going to and if the distances are becoming smaller and small, then obviously they are going to converge somewhere, because the distances are becoming small and small. And that's the definition, the distances are becoming small and small. And that's what we use this mod sign here, because we are representing a distance, that is xn minus L. We are calling it a distance. So the distances between the numbers and the limit, it becomes smaller and smaller and smaller and smaller. Okay. And for instance, in this case, let's say if we have 2 power n. Now, what about this one? So first term is 2, second term is 4, third term is 6. Oh, sorry, it's 8. 2 cube, it's 8. It's 8, then 16, and then moving on and on. Now, can I find a number, a limit for this thing? I cannot find a limit because I can see that if, for instance, I say that I claim that some number is the limit of this sequence, and I want to find the distance L with that number, distance of each point with that number, and I can see that the distances will be bigger and bigger. Okay, the distance will become bigger and bigger, and it's not going to converge anywhere. So it's bigger and bigger, and it's going towards infinity. So these kind of sequences cannot be convergent. They are not going to converge at any point. So these sequences, these kind of sequences, does not qualify this definition. So the intuition behind this definition is that we are checking the distances, that as much as we are going bigger and bigger, we are going to get smaller and smaller distances with the limit point. That is, we calling limit L here. Now, if limit n tends to infinity, xn equals L, we say that xn converges to L. So that's the convergence, and we call it converge, that the limit is converging. So, and we call it convergence of a limit of a sequence. Okay, and we write it as, this is the notation that xn converges to L, simply by making an arrow that xn will be going to L. And if there is no real number to which xn converges, we say that xn diverges. It's simple. And if there is no number that it's converging, we call it a divergent sequence. So there is some statement that it means we show that corresponding to an arbitrary positive, a real number epsilon, after a certain number n naught. Okay, we already talk about this. After a certain number n naught, there's a certain n naught, that after that n naught of terms, all the remaining terms of the sequence will be within a distance epsilon from L. So that's what we mean by xn minus L is less than epsilon. So all the terms after a certain n naught will be within the distance epsilon from L. So we are taking distance from L for each term here, and somewhere, after some n naught, we are going to get these distances in the range of the epsilon, that is within the epsilon distance, within the epsilon distance. Okay, so now limit x tends and tends to infinity, xn equals L. It means that xn can be made arbitrarily close to L by making n sufficiently large. So we can make this xn very close to L. As we are taking n bigger and bigger, we are moving on and on. We already discussed about in the case of the sequence. We talk about a sequence as an example here, that as we are moving on and on, going bigger and bigger, we are making the distances to be lesser and lesser. The distance, what distance? The distance of the numbers with the limit of the sequence, it will be lesser and lesser, and it will be less than epsilon after some and not. Okay, so now consider an example that is limit n tends to infinity, and 2n plus 3 over 3n minus 7 equals 2 over 3. Okay, we are claiming that the limit of this sequence is 2 over 3. Now, the question is that, for understanding, I've taken this question that after how many terms we are guaranteed that this sequence is within a distance of 0.01. That is, now in this case, I'm taking epsilon equals 0.01. Okay, so I'm assuming, and I want to see that after how many terms, I can get the epsilon distance, the distance that is xn minus L less than 0.01. So I want to see that for my understanding. Okay, let's start that we want an n naught belongs to natural numbers such that whenever we go beyond that n naught and we take any n belongs to natural numbers, this will imply that this thing here, that is xn minus the limit L, is less than this epsilon that I am taking here, 0.01. So let's solve this problem. We take LCM here, that's the least common multiple, and we already know how to solve this thing here by taking the LCM and then simplifying. So it's inside the modulus and it's less than 0.01. Now this is 23, it's a constant number, so I can remove the modulus from here. It's not a big deal. But from here, I'm not removing the modulus because this is 9n minus 21 and it can be negative as well and positive as well. So that's why I'm not removing the modulus from here. And still it's less than equals to 0.01. Okay. Now what I'm doing is I am taking the reciprocal, and whenever I will take the reciprocal, the inequality sign changes. That is the rule, that is the theorem we already have learned in the previous lessons, that if I take the reciprocal, then the inequality is going to be changed, and now if it was less than, then it's now greater than, and I will multiply this 23 on the right side, then I'm going to get 9n minus 21 greater than 2300, and then I square both sides. I square both sides because I want to find n. So I want to remove this mod first. To remove this mod, I am squaring both sides. So I get this squaring this mod and this on the right side. Then I take this to the left side. I solve this quadratic equation to find the value of n. So here I get two values because it's a quadratic equation. So n is greater than 257.889 and is greater than negative 253.22. So n is greater than negative 253.22. This makes no sense because it's a negative 253.22. So every n is greater than negative 53 because n belongs to the natural. So every n is greater than this number. So this doesn't make a sense here. So we'll take this number here, that is n greater than 257.889. So what does it show? It shows that this thing here is now my n naught. So if I approximate this, so it's approximately 258. So I can say that whenever my n is greater than or equal to this number 258 here, then the sequence, the terms of this sequence, any term, for instance, if I take, let's say we take 259, so 2 times 259 plus 3 over 3 times 259 minus 7 minus 2 over 3. Now I'm going to calculate this distance and I can show that this is less than 0.01. That is what was my epsilon. That's what was my epsilon that I assumed in beginning. Okay, so it's 2 times 259 plus 3, sorry, that's 2 times 259 plus 3. Let's calculate this. So it's 521. Then 521 divided by 3 times 259 minus 7. That's 0.67. Okay, that's 0.67. So this thing here, this thing is 0.67. So I can write 0.6766 and so on, minus 2 over 3. So 2 over 3, we all know that it's 0.66666. Okay, 0.666, so on, and it's in the mod. So if I subtract this 0.66 by 0.6766, so I'm going to get 0.0099 something, and this is surely less than 0.01. Okay, so this thing here, this distance here, this whole distance becomes less than this number 0.01 after this n naught. Okay, so that's what we are talking about in the terms of limit, and it's the essence of the limit that the distances become smaller and smaller. And I can also solve by taking epsilon equals to 0.00000000001. And I can see that there will be some n naught. For instance, it will be 23 million or 23 billion, that after 23 billion terms, I will be in the range of, my distance will be in the range of this epsilon distance. I will be in the range of epsilon distance, this epsilon distance. So epsilon is a small number, positive, it's greater than the 0. And I can assume as small as I can. So this condition should be verified every time for the convergence of the limit. Okay. Similarly, we can work out for an arbitrary epsilon. Okay, we can work out for arbitrary epsilon just like we work out here for 0.01 in the similar manner. Just we can do this again, and again this we take less than epsilon. Now we are not assuming a number just like we did in the previous example, that's 0.01. Now we are saying it's arbitrary. Okay, again doing the same thing, taking the reciprocal, and to remove this mod, taking the square, because it's 9n minus 23 and the mod can be negative, can be positive. So it's 9n minus 21 squared. I get this thing here, this thing on the right side. I take it to the left side like this. It's a quadratic equation. I solve the quadratic. The A is 81, B is negative 378, and C is 441 minus 520 over epsilon squared. I solve this inequality and I get these two values, that is n greater than 2.33 plus minus 2.722 over epsilon. So again, there's a negative sign here. So we don't need any negative numbers in our case. So and this is negative, and if epsilon is very lesser and lesser, and we know that this number is always going to be negative, and we don't need negative n, because n is natural number, and we know that the natural numbers are all bigger than the negative numbers. So we will only talk about the positive numbers. So we get this thing here, that is 2.33 plus 2.772 over epsilon. So this is my n naught. Now for every n greater than or equals to this n naught, this definition follows that xn minus L will be less than epsilon for this particular sequence that I'm talking about in this example. That is this sequence. Where is sequence? That is this my sequence. 2n plus 3 over 3 and minus 7. That is my sequence. Okay. So that's the general case for this sequence, and we showed that we can work for arbitrary epsilon for any sequence. Now we are talking about algebra of limits. Suppose xn is a sequence, then xn converges to 0, that is xn is converging to 0, implies that xn, that is the sequence, mod of xn is converging to 0, that's the distance is converging to 0. And xn converging to L means that xn minus L is converging to 0. Okay. And xn minus L implies mod of xn minus mod of L. We can just remember these are simple things that we already talk about. That xn, if we say that if xn, it's like that if xn equals to L, then surely xn minus L equals to 0. So these are something like simple, it's algebra, not very complicated. Now constant sequence, we already talk about a constant sequence. It's a sequence that a sequence xn is called a constant sequence if there exists some constant c belongs to the real numbers for all n belongs to n, xn equals to c. So if I take the sequence 2, 2, 2, 2, 2, and so on, so it's a constant sequence. In this case, my c is 2, and c belongs to the real numbers. And it might be 1.6 like this also, 1.6, 1.6, 1.6, because we are saying that c belongs to the real numbers, such that for all n belongs to n. So whatever n I am going to take here, I am going to get the constant term 2, 2, 2. Okay, so it doesn't make any difference, the n here in these kind of sequences. So we call it constant sequence. An example is here, that is 1 over n equals 1 power n equals 1 1 1 1 1. That's a constant sequence. And a constant sequence converges to the sequence, the constant itself, right? Whatever constant we have, the constant sequence is going to converge at that point. For instance, the point of convergence, that is the limit of this sequence, is 1. Okay. A sequence Xn is said to be eventually constant if there exists C belongs to R and there exists N naught belongs to N, such that for all N greater than equals to N naught Xn equals to C. So a sequence, we can call it eventually constant if after some N naught, that after some terms, it becomes constant. For instance, this is a sequence 1 over half, 1 over 3, 1 over 1 4, and 1 over 1 8. And after some infinite terms, or after some terms, it becomes 1 1 1 1 1 1 1 and dot 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 dot. So we call it again, we call it eventually constant sequence. Okay, so there is some n naught somewhere here, some n naught, that after that, sorry, somewhere here n naught, my n naught is somewhere here, that after that the sequence becomes constant 1 1 1 1 1. Okay, now we have fundamental limit, that is limit n tends to infinity 1 over n equals to 0. We are going to prove this statement by using the definition of the limit. Okay, so let epsilon greater than 0, then 1 over epsilon is greater than 0. Pretty simple thing. Okay, because epsilon is a positive number, and if I divide this positive number, I divide 1 with this positive epsilon, then obviously I'm going to get a positive number that will be greater than the 0. And then by Archimedean property, we know that there exists n naught belongs to naturals, that we have a natural number that is always bigger than a real number. So we will always have n naught greater than 1 over epsilon. That's by the Archimedean property. So there is a natural number always bigger than the real numbers. So this n greater than equals to n naught implies that n is greater than 1 over epsilon, because we said that n naught is greater than 1 over epsilon. And then we are also claiming by definition that n is greater than equals to n naught. So by these two inequalities, we can say that n is greater than 1 over epsilon, because if n naught is greater than 1 over epsilon and n is greater than n naught, then this thing is true by the properties we already learned. So it's just like if x is greater than y and y is greater than z, uh, x is greater than y and y is greater than z, then no, sorry, not like this. If x is greater than y and x is greater than y, and then we have z is greater than x, okay, then we can say that z is greater than y. It's like this. So now we can say that if n is greater than 1 over epsilon, then this thing implies that 1 over n from here, if I take reciprocal, so 1 over n, it will be obviously greater than 0. That's obvious that it will be greater than 0, but it will be less than epsilon. Okay, because the inequality changes. I have already told that when we take the reciprocal, the inequality changes. So for instance, first we write it like this, that we take the reciprocal and the inequality is changed. This is lesser than epsilon, but we know that this is always greater than 0. It cannot be negative, it's positive. So we write in this way, 0 is between sorry, 1 over n is between 0 and epsilon. Then we can just write this thing in the modulus in this way, that 1 over n minus 0 will be less than epsilon. Okay, so because if we want to if we can subtract the 0 from both sides, so 1 over n minus 0 less than epsilon minus 0. So uh, we apply mod 1 over n minus 0 is less than epsilon. This is obvious. This is simple algebra, right? We already have talked about these inequalities. You can check and verify this thing. Okay, and this we can also take in this way, that if this 1 over n is greater than 0, then we can say that 1 over n is also greater than negative epsilon. We can write in this way, because if it's greater than 0, it's already greater than negative epsilon, right? Because a negative epsilon will be lesser than 0. So we can also write in this way. And when we conclude this uh, this mod, then we can say that or we just don't need to write in this way. It's fine. Keep it like this. We don't need to do that. It's fine that we are done here, that 1 over n minus 0 is less than epsilon in the mod. Okay, so this was the result that we want to show, that the xn minus L is less than epsilon. So it's proved. It's called the fundamental limit. So in the next class, we will talk about the uniqueness of the limit, and then we will take some theorems on the limits and convergence. We will talk about the convergence criteria, the Cauchy's criteria, and some other topics as well. So thanks for watching the lesson. That's all for the time being. Goodbye.